Hi, I'm Chris Wicks, your fellow Calc 3 classmate, and I'm going to be doing the bonus problem from one of the homework assignments. I think it was the first or second chapter 13 homework. Anyhow, I figured possibly some of you didn't get to the bonus or you didn't figure it out, and there's no answer key, so I'd go over the problem. That's a good illustration of the chain rule as applied to a word problem. The problem reads, a boy's toy boat slips from its string at the edge of a straight river. The stream carries the boat along at 5 feet per second. The crosswind blows it toward the opposite bank at 4 feet per second. If the boy runs along the shore at 3 feet per second following his boat, how fast is the boat moving away from him when t equals 3 seconds? Show a clear diagram in all work showing how to calculate the answer clearly using a function of two variables and the chain rule. Include exact and approximate results. So the first step that I took in solving this problem was just drawing a picture to kind of get a feel of everything that's going on here. Now, as you can see, we have our sad boy here. This is our very straight, ruler-edged river with a current at 5 feet per second in what we're calling the positive x direction, and the wind's blowing at 4 feet per second in what we are calling the positive y direction. And then the distance between the boy and the boat, which is what we are seeking out, we are going to be trying to find that at t equals 3 seconds, is represented by d here, which, as you can see, forms a right triangle with x and y. Hint, hint, we're going to be using the Pythagorean theorem. Anyhow, the first step is to come up with functions of x, y, and d. First of all, we can get functions of x and y with respect to time pretty easily here. X is going to equal 5 minus 3t equals 2t feet. So basically that's saying at any given time, basically x is moving at 2 feet per second. The way we come up with that is that the boat is moving in this direction at 5 feet per second. The boy is moving in this direction at 3 feet per second. We take the difference, 2, obviously, and that is going to be our change in x. Now the change in y is obviously just 4t feet. Our function of y at t is going to be 4t feet, with t being the number of seconds since the boy and the boat parted ways. Now, the next step is to find a function for d, and that's pretty easy. That's just, as I said earlier, we have x, y, and d forming a right triangle, so d is always going to be the square root of x squared plus y squared. I have it written here just in that format with the 1/2 exponent just for easier partial differentiation. So, the next step, we're going to differentiate the functions of x and y with respect to t. dx dt is going to be, this is pretty straightforward, 2 feet per second, and dy dt is, again, very straightforward, 4 feet per second. Next up is we need to take the partial derivatives of d with respect to x and y. So, partial of d with respect to x is, first, of course, you bring down the exponent. The 1/2 exponent comes out front. We decrement it to negative 1/2 in the exponent there and leave the x squared plus y squared in the middle. Then, as per the chain rule of differentiation, different chain rule, still chain rule, we take the partial of the inside. We take 2x is going to be our partial with respect to x. So we end up with x over square root of x squared plus y squared feet per feet. I was a little fuzzy on the units here. As you can see, I've got some tape and paper. I redid it a couple times, but I'm pretty sure it's feet per feet because we're changing x and getting the resultant change in d. And so we're changing the feet per feet. If I'm wrong about that, anybody, please don't hesitate to chime in on that one. Next up, pretty much the same process.
the partial derivative of d with respect to y ends up as y over the square root of x squared plus y squared feet per feet. Moving on to the next page, I've got all our values. The solutions are derivatives and partial derivatives of our functions from that we just got through our work on the previous page. Now we need to use a chain rule. Now remember that the chain rule says that the change in d with respect to time is going to be the change in x with respect to time times the partial change in d with respect to x plus the change in y with respect to time times the partial change in d with respect to y. Note that you're kind of canceling out dx, dy, dy here. It's kind of a good way of thinking about it if it's not 100% logically sound. It kind of makes it easier to think about it that way. So you end up with the change in d with respect to time and the change in d with respect to time. The sum of those two partials is the total change in d with respect to time. Now, from here on out, it's pretty much just plugging in values. So, first of all, we just take our derivatives, plug them into that equation. We have 2 times x over the square root of x squared plus y squared plus 4 times y over the square root of x squared plus y squared. Now, we need to go back to our functions of t from this part. Remember, x equals 2t, y equals 4t, and plug those values in. So, x is 2t, y is 4t, x, y, and notice that I combined, since it's the same denominator there, we just combine denominators and combine the numerator, no problem. Combine the denominator, it's the same denominator. From there, we just solve and simplify. 4t plus 16t is 20t, 4t squared plus 16t squared is 20t squared. Pull out the t and the 4 from there. Square root of 4 is 2, square root of t is t, and you're left with the square root of 5. Now, to simplify, the t's go away, the 2 goes away, we're left with 10 up top, and we rationalize the denominator, we're left with 10 radical 5 over 5, simplifies to 2 radical 5 feet per second. Now, to get a more immediately intuitive result, if not 100% accurate, we get 2 radical 5, 2 square roots of 5 equals 4.47213595, or about 4.472 feet per second. In conclusion, at any given time, including t equals 3 seconds, the boat is moving away from the buoy at 2 square roots of 5 feet per second, or approximately 4.472 feet per second, which is what we were asked to find in the problem. Alright, I hope you found this useful.